Hello, and welcome to Aggressive Physics. Today is day 15, and today I'd like to look at a problem set that is a little more complex than the ones we've been dealing with so far. This is more of an honors-based problem set, and what it's going to involve is a scenario where we have an object moving with two different types of motion during the entire event. And I think today we'll look at a 100-meter dash, where an object will, or in this case a person, will start at a certain rate of speed and then travel at a constant velocity for the remainder of the problem. Now these problems are extremely complex, and those who are in a Regents course or an introductory course may find that this is a little more difficult than the problems that they're used to. It involves algebraic solutions that are slightly complex. Effectively, we're going to be using simultaneous equations, possibly substituting one equation back into the other. So for some of us, this will be a little more advanced than we'll be expected to do on an assessment. However, I'd like everyone to realize that these problems can be solved, that this type of complex problem has a methodology that can be useful for all students, and what's important to realize is that the object, although it has two types of motion in an umbrella of a single race, we can treat it as two separate problems. The problem where the object is starting from rest and accelerates, and then the problem where the object is moving at a constant velocity. And there's one key to solving any problem like this, and this is a very complex topic, very difficult to grasp the first time, but it's the fact that the final velocities of one scenario or one section of the problem will become your initial velocities for the next section. Now as we move forward in the course, you'll see that we'll do a number of problems like this. For example, let's talk about a diver jumping off a diving board. When the person jumps off the diving board, they're traveling through air. As soon as they hit the water, the problem becomes a unique problem. We've been solving for final velocity for many problems in the single kinematics equations. However, realize that the final velocity is not what the final velocity of the object actually is, because at the end of the problem, the object will be stopped. What we're looking at is the final velocity under the condition where it's experiencing uniform acceleration. In this case, falling through the air at a negative 9.8 meters per second squared. When a diver hits the water starts a new problem. And what we'll be able to do is use the final velocity of the diver in the air to become the initial velocity for the diver in the water. So some variables will have multiple purposes within a complex problem. So in this case, be mindful of the variables that will go from problem 1 to problem 2. In this case, it will be the uniform acceleration problem when the sprinter starts from rest. Then will become the constant velocity problem once they reach a specific speed. So let's look at this kind of practice problem. All right, this problem is going to be a little harder. So what I want to do is introduce our new helper here, Mr. Fizz, to help us with this following one. Remember, this is an honors problem where we're going to have multiple solutions in order to get the answer. In this case, it'll be a substitution method, and we're going to take two equations and set them equal to one another. So what's happening in this case is Mr. Fizz here is running in the 100-meter dash, and he's trying to break the world record. The world record is 9.58 seconds. And it's a 100-meter dash. And what's important to realize for this problem is that there's going to be two sections. A section where he accelerates, and he's going to move at 3.4 meters per second squared. And then he's going to have a section where he has a constant velocity. But we don't know what that is. Now this is the first problem we're going to deal with where we need to use the final velocity of one section as our initial velocity for the next. So what we'll do is set up our givens list using two parts. And this will be important again when we do the projectile motion section shortly. We have the accelerated part, and we have the constant velocity part. Now, when he's accelerating, he's going to start from rest, so VI is 0. His acceleration was given as 3.4 meters per second squared. What we're going to have to do for this is we don't know how long he takes to do this section, so we're just going to call it t equals t. You'll see why in a second. We also don't know how long it takes in terms of the distance he travels, so we're going to say d equals d. You can call it x and y if you wanted, but I'll stick to the variables we already know. The other thing I know is that we're going to need to find VF, and that's because this VF is going to turn into VI for the constant velocity. Let's say he stops at the acceleration at 7 meters per second. Well, that's the initial velocity he'll have for the rest of the trip. And since that's for the rest of the trip, that's also his V average, because his acceleration, if he's going at a constant velocity, is 0. Now, this is where the d and the t come in handy. The t is going to be 9.58 minus whatever the time was for the accelerated part. So I'm going to write it as 9.58 minus t. The d is going to be whatever section of the 100 meters he took minus the d from the first part. So I'm just going to call it 100 minus d. Now that concludes the setup for the problem. What we'll do now is find 3 equations that will allow us to solve for the final results. And what I'm going to do is call them A, B, and C. A and B are going to be part of the accelerated motion. C is going to be part of the constant velocity. Now for the acceleration, we know VI, we know A, we know T, and we know D. And what we need to find for these is the distance and the time, effectively. So we need to have equations that have D and T in it. But importantly, we're also going to need to know VF if we're going to use it for the second side. So this VF will become important. It's the one variable that's going to jump the chasm between the two givens lists. So for equation A, I set up equation 4. D equals VIT plus 1/2 AT squared. Now the D I'm going to plug in as D. VI and T cancel because there's a 0. 1/2. The acceleration is 3.4 meters per second squared. And we don't know T, so we're just going to set up as T squared. So right now we have 2 unknowns. To find VF, we would use equation 3. VI plus AT. Now VF, I don't know. VI is 0. A is 3.4 meters per second squared. And T, well, we just know it as T right now. So VF equals 3.4 T. And this equation is going to allow us to solve for the 2 equations coming together. Now, for equation C, since it's a constant velocity, we're just going to use V equals D over T. But we need to use the variables from this side of the equation. Now, V happens to be this 3.4 times T. So what I'll do is I'll set it up as 3.4 meters per second squared times T. I'm substituting that equation in for V because the final velocity is the velocity for the rest of the problem. And then the D is 100 meters minus D. And the time, 9.58 seconds minus T. Now these 3 equations, equation A right here, equation B right here, and equation C right here are going to allow us to solve for D and T. Now here's what's important. We've already substituted B into C. Now what we need to do now is substitute A and C. Well, what I'll do instead is, since I think we'll be able to rearrange for D and maybe set them equal to each other. Since I ran out of room on this page, we'll reset with the 3 equations and we'll solve from there. All right, now that we have a little bit more room, what we'll do is rearrange equation BC and make it a little more useful to us. What I'm going to do first is cross multiply the 9.58 minus t times 3.4t. So 9.58 minus t times 3.4t is going to equal 100 minus d. I have to multiply each of these terms by 3.4t. So if I do 3.4 times 9.58, I'm going to get 32.572, and the t stays, minus 3.4, and then t squared equals 100 minus d. And I guess the easiest way to do this is I'll set it up and set it equal to d. D equals, I'll bring the d over, and I'll bring these two terms to the other side, 3.4 t squared, I'm bringing that over, minus 32.572 t minus 100. The d was over, that became a positive, the 100 stayed, whoop, that should be a positive 100. The 32.572 comes over, so that's a negative. The 3.4 comes over, so that's a positive. Just making sure the units are correct and the signs are correct. Now, this has a d and equation A has a d. And what we're going to do is set them equal to each other. So what I'll say is equation A equals equation B slash C. So 1/2 of 3.4 is 1.7 t squared. That's equation A equals, and I'm going to plug in all this stuff here, 3.4 t squared minus 32.572t plus 100. I'll bring over the 1.7 t squared, and that will subtract from the t squared there. So you'll end up with 1.7 t squared minus 32.572t plus 100 equals 0. And to me, that looks a lot like a quadratic equation. In fact, what we're going to do is substitute that into the quadratic. And when we do that, we should get two roots. And the two roots are going to be 3.84 seconds and 15.32 seconds. Now, if we think about it, the scope of our problem ends after 9.58. So this 15-second term is too big. So the t is going to be 3.84. Now, how can I figure out what the d is? Well, I could take this t and I could substitute it back into the first equation. And if I do d equals 1/2 3.4, and that was meters per second squared, times 3.84 seconds squared, I should get the distance I traveled before I started moving at a constant velocity. So if we use the calculator, 0.5 times 3.4 times 3.84 squared, and I'm going to get 25.07 meters. So that means the acceleration occurred for 3.84 seconds, and the distance was 25.07 meters. That means the constant velocity had to be 9.58 minus 3.84, or 5.74 seconds. And 100 minus 25.07 should get us 74.93 meters. So all told, we have four answers. For the acceleration, we went for 3.84 seconds and traveled 25.07 meters. For the constant velocity part, 5.74 seconds and 74.93 meters. Now this type of problem is a little complex, as you've seen. That's why I consider this an honors problem. But what's important to realize is that the final velocity of one section becomes the initial velocity of the next, And if you look at the entire scope of a problem, you can break it into smaller pieces by calling some variables d's, in this case for distances, or t's for time, and subtracting for the second set from the grand total. So this is a difficult problem to solve, yet if we think of it in smaller pieces, can become feasible.